Alright, so hopefully I have this on screen properly. Are the max and mins there? Oops,
Yeah.
no. Are they on screen? Is my finger on the screen?
Yep.
Okay. Alright, so this is called a stable distribution, or a Levy stable distribution. And it has a parameter that you can vary, let's call it, say, between 1 and 2. And this is the kind of thing that Taleb is talking about. So this is in between the extreme variation in the Cauchy distribution and the minimum variation in the normal distribution. In fact, when I hope this doesn't jump around, when I put the parameter equal to 2, and I'll just do 100,000 runs.
It's more.
I gotta lower the camera a little bit rather than just playing with the screen. You see, in 1,000,000 runs, when they put the parameter equal to 2, I stayed pretty nearby.
Yeah.
Right? I didn't have the huge extreme variations, and it seems pretty consistent. If I do 10 million runs.
So 2, they're just a little larger.
Okay, so what do you think? What would you say when I put the parameter equal to 2? Could we rule out that this was a normal distribution?
No, it looks similar, but there's more variation.
Just a tiny bit more variation.
Yeah, so it might be just a normal distribution that's a little bit wider than what we had seen before. But we certainly can't rule out that it's a normal distribution. But now I'm going to change the parameter, let's say, to 1.8. And we're going to start small. We'll start with 100. So what would you say here with this distribution? Tell me about what you see.
Well, we've sort of got just like one large column, a few sort of medium columns, and then some outliers.
Okay.
And the minimum and maximum aren't really so close to the tall column.
Do you think we could rule out a normal distribution here?
Not entirely. I mean, we don't have enough data points. Maybe we just have an outlier. And
Okay, yeah. So with the normal distribution, we saw stuff that even got down to -7.
mm-hmm.
So who knows? Maybe we just got this incredibly rare event, and we don't know for sure. We can't quite rule it out. Right? What would you suggest we do to see if this looks like a normal distribution?
Probably up the number of runs.
Okay. How many would you like to try?
Maybe 1,000,000.
1,000,000? Okay. Let's see. All right. What do you think now?
Well, it's kind of like almost looks like a normal distribution, but the minimum and maximum are really far away.
Those are really wide, so I don't think you can make the case that this is a normal distribution.
Okay, you don't think we could make the case that this is a normal distribution. So what would you say is different about this?
It's wider. It's much wider.
Okay. Yeah, and you were talking about measuring the width using this concept of standard deviation.
Mm-hmm.
And so we could measure, if we wanted, I mean, we could take a standard deviation, which is just a calculation. When you only have a finite number of data, we could do the calculation for it, and we could compare how far away those things are and say, hey, well, maybe that doesn't look too good. So this looks different than a normal distribution. The really tricky thing is figuring out if we can tune this parameter. So could we say, what does it look like instead when it comes from something where it's 1.5? So I'll do 1,000,000 runs with 1.5. And what do you notice that's different now?
So this is starting to look more like the
Cauchy.
the one we saw before. We have
Okay.
2 massive stacks, and then that contain basically the entire data set, and then outliers that go on forever, or for a long time.
Okay, that's interesting. So do you think we could eliminate this as a normal distribution?
Yes.
Okay. Do you think we could eliminate the Cauchy distribution?
No.
Here?
It
Alright.
just looks a lot like the Cauchy
It's a
distribution.
thinner version of the Cauchy distribution, but it still looks like it.
Okay, so why do you say it's a thinner version?
Well, when we were at 1,000,000, or I think we were at 10,000, we had numbers bigger, or still slightly smaller than this at 10,000. So at 1,000,000 we should have, or 10,000,000 we had like 10 to the 6th.
All right, let's see what we get at 10 million.
So we're getting smaller numbers. So it's
Yeah.
we could either say it's a really thin normal distribution, or really wide normal distribution, or a really thin Cauchy distribution.
Okay, so do you think this could be a normal distribution?
No, because it's too wide, and
Okay, why? Why? Tell me again why you think it couldn't be. Like, look at the
Because
max and mins here.
the max and mins are just too far away.
All right,
Like,
what
if
is
this
the
was
max?
if this was a normal distribution, the max is 103,000.
Yeah.
So if this was a normal distribution, the max would be like 7 or something.
Okay. Yeah. It's not even clear how wide this is, but like, because these extremes are so far away. Now, do you think it's a Cauchy distribution? Can you tell me?
No, because the maximum and minimum are too close to our two really tall stacks. I mean, we didn't even do 10 million runs with the Cauchy, but with 1 million, they were like 4 million and negative 11 million.
Okay, interesting.
So these ones are too close.
Yeah, let's take it down to 1.2 and look how wide that is.
Yeah, it's approaching what a Cauchy distribution would look like.
Well, yeah, maybe. Although notice that it's not actually that much different than 1.5. Right, the max
Yeah.
was a few 100,000, and with the Cauchy we were in the millions. So 1.2 to 1.5 didn't seem to change that much, which I think shows you that it's difficult to, back to what Taleb was saying, it's difficult to know what distribution we're looking at, but we've been able to rule out a normal distribution, we think.
Yeah.
And could this be a Cauchy distribution? What do you think?
We don't really think so because the maximum and minimums are too close together.
Yeah, and I might be remembering wrong, but at 1.5, I think on this one, but we're at 1.2. At 1.5, we're even wider. So it's really confusing. You really need an enormous amount of data. Even 10 million doesn't seem to be enough to distinguish between 1.2 and 1.5 for whatever that parameter describes. But I'm going to put it at 1.01 now. Let's see what we see.
And now we're
Now we're
seeing our really large maximum and minimums.
Yeah, so here maybe we could eliminate 1.5 and 1.2 if we saw this data, these 10 million points of data. And it's starting to look a lot like that Cauchy distribution. So this is the central problem that Taleb is talking about. That it's very difficult to know what distribution you're looking at. It's a very hard problem. But sometimes it's easy to eliminate certain distributions. So like when you're looking at wealth, what do you think, what kind of distribution do you think you're seeing between a Cauchy and a normal?
it would be a Cauchy.
Might look more like a
Yeah.
Cauchy distribution, although we don't know.
It wouldn't be a normal distribution though. It wouldn't look like.
And when you're looking at height,
It would look more like a normal.
it would look more like a normal distribution. So sometimes understanding what you're looking at helps you eliminate certain kinds of distributions. The real tricky thing is in the middle. Like if you're looking at earthquakes or floods, all of a sudden, or volcanoes like we saw in Iceland, all of a sudden you could have a single event coming in the future that changes the entire distribution in terms of like the damage it does. So it's cool. So this is a hard problem in statistics, and we're doing kind of a high flyover, but what do you think? What do you think about this?
Yeah, it's pretty cool.
What do you think?
It's pretty cool to kind of see, I guess, how hard it is to distinguish two things.
Yeah, that's important to keep in mind when you're trying to do analysis of what sort of things you're looking at. All right, good job, guys.